I can. Okay. So welcome. It's great discussions this morning. So I'm going to talk about HDF in the cloud and some ideas and projects the HDF group is working on. So HDF5 data format. So with 20 years of history of HDF5. And for those who don't know, NetCDF4 is actually HDF5 under the hood. So if we can solve the issue of HDF5 in the cloud, we're also solving it for all NetCDF4 content. And so when HDF5 was designed, it was designed both as an archival format, so data that can be preserved for decades, but also be analysis ready, meaning that you don't need necessarily to convert it to something else to do analytics. And over the years, there's a very rich set of software and tools that developed around HDF5. And this editorial opinion is that before we go off to find some other file format, we should think long and hard. Do we really want to abandon not only the petabytes of data that exists now in HDF5, but the entire tool chain, et cetera? So the challenge of HDF5 in the cloud, and a lot of the previous speakers have touched on this, when you put an HDF5 file stored in S3 object, you can download it again, but you can't directly read that object with the HDF5 library. And this has led to interest in formats like ZAR and TileDB that allow data to be accessed in part when it's stored in the cloud. So recently, we developed a plugin for the library. This is a kind of plugin at a very low level of the HDF5 library that lets you pass a handle to the S3 object. And that from then on, you just read it just as you would a regular HDF5 file. So in the library, every call that normally be a POSIX read gets translated to the S3 range get. This is like pulling out a piece of the S3 object from S3 and back into the library. This will be available in the next release of HDF5. It's the first release. I think there are many more things we want to do as far as performance improvements and such. And we really should be collectively as a group, I think, looking at benchmarking this usage versus other ways of accessing HDF5 data in the cloud. Especially since Amazon's changed the performance envelope this week. So if we're going to put HDF5 data in the cloud, and so we just had to talk about Cumulus, right? So petabytes of data are going to be placed into S3 buckets. It would really be good to think, how can we optimize that content so that when it's accessed, rather than just being downloaded the entire file, that access is performant. And there are various things that I think would make sense. One is always use chunking, so you have the availability to pull in just chunks of data, not the entire data set. There's some discussion about what kind of chunk layout. If you don't know what the access pattern to that data will be, it's probably the least worst to have a kind of a qubit shape of chunks. Use compression filters that are readily available to the client. And if we can pack all the metadata in the file to the front, that will reduce a lot of the round trips between the library and S3 in getting metadata before it can be able to start reading the data set content. All right. Okay, next, I wanted to talk about HDF Server. So this is a REST-based service we've created for HDF data in the cloud. So it's HDF data, not actually HDF5 files. So it's a bit of a distinction. The server runs as a set of containers on Kubernetes. So that means we can run containers that are spread out across multiple machines. And this gives us a flexibility to be not only like high level of client demand, but to parallelize access across different chunks. So when you do a request to the server, that server can send, hundreds of requests simultaneously and pull in S3 data. And so you get a lot more throughput and performance that way. And it's available now. You can go to hdflab.hdfgroup.org and try it out in a Jupyter environment. Okay, so what we do as far as taking regular HDF files and making it available in the cloud is that we break up that content. So we take all the metadata, we store it as JSON objects, and chunks get stored as binary blobs in S3. So if I have, say this rectangle is a data set and it's chunked, so the dark lines represent chunks, each chunk gets stored as a separate S3 object. And when, say, I want to read this yellow rectangle, that crosses 6 chunks, so 6 S3 objects. But the server is going to pull all the data together for you and return it to just what you want. So as a client, you don't need to worry about how these individual chunk objects are stored in S3. The metadata, for example, data set with a type and layout and such, is stored as a JSON text in the S3 object. So here's an example of how we represent a data set. So I had this great thing here, how we distribute keys across the namespace in the bucket for performance, because until this week, there was a limit to 300 requests per second per bucket. But then 2 days ago, Amazon raised that from 300 requests per second to 5,500 requests per second. So that argument doesn't really work so well anymore. One other thing we do is that we don't have like a directory of chunks. The chunk keys are determined dynamically based upon what portion of the data set you're accessing. And currently, the only tools we have for accessing this content is through HDF Server. But there's nothing to prevent reading that data directly. And we published the schema. So if you have, if you want, say, have a distributed process that's doing lots of reads, and you don't want to go through a server, there's an ability to get that data directly from S3. Okay, now I'd like to talk about how could we do this for traditional HDF5 files as well. So it's great, we can take an HDF5 file and we store it in this new fangled way. But if you have tons of data already in S3, for example, I want to access Cumulus data, I may not really want to replicate that data again to store it in a different format. So we've been thinking about this idea of we pull in just the metadata of the source files. And then access to the chunks is again through the range get. So now you have the best of both worlds, right? Because you have fast access to understand the metadata of the file, and the bulk of the storage still resides in the original HDF5 file. So here's an example of how it works. So imagine I have an HDF5 file here stored in S3 object. I run the importer that grabs all metadata that stores in S3, and the server access would do the usual stuff until it got to reading a chunk from a data set in the file. And here, this access would get translated to the S3 range get. So given the key and the offset and num bytes, this metadata knows that this chunk here is at this offset from the file and it's this long. It can directly read that content. And here are some references. And now, since I talked so fast, I have time to do a little demo. So here's HDF lab.hdfgroup.org. And so I'm running a Python notebook in AWS. And let me put that larger. So I import this package we have, h5pyd. And from this point on, everything here is exactly the same accessing HDF server as would be accessing a regular HDF file on disk. Except when I do this, this path name is actually not a POSIX path. It's a request that goes to the server. The server fetches the metadata from S3, returns it back in the H5Py compatible format. And you can see this because the ID, and normally an HDF library would be a numeric ID. Here it's a string, it's a UID. So in this file, there's a data set, and its shape is 8,000 by 8,000 by 3. So it's 120 megabytes. And the chunk shape is 500 by 1,000 by 3. So there are 128 S3 objects that represent this data set, and they're just kind of scattered through S3. If you look at the S3 bucket, what you see is a bunch of hard to interpret UIDs, right? So these are all the flat things, they're all this showing up there. But the server will be able to get you what you need. So here I'm going to read a 3 megabytes from this data set. And I'm going to say, let's get every 8th point in the first 2 dimensions. So I do this, and that returned in 268 milliseconds. And I can do a plot of that. And we have this nice copy of blue marble. Okay, so the entire data set is 120 megabytes, but because I selected this subset of it, I was able to get that pretty fast. And if I want to be kind of zoom in on a subregion, here I'm going to say get this portion of the image, but don't subset it, just get the full resolution image. And then that works. That returned in 54 milliseconds. So 54 milliseconds. So we talked about latency. So here, my notebook is talking to HDF Server, which is talking to S3, getting a bunch of objects, coming back to the server, coming back to my notebook, and getting displayed. But it's maybe slower than using HDF library on a local SSD drive, but it's quite reasonable performance. Okay. And I have 1 minute left, so I can do this. I can say, so we have a bunch of tools here. If I do, so I can list content. So here's a HSLS. It's like H5LS, except it's looking at content on the cloud. If I do HSLS, I can see a bunch of content I have. So the content is available, and it's multi-tenant in that you can control permissions at the file level, even though it's all co-resident in the same bucket. All right.